So now we're going to look at a couple of key examples of the process for working with potential energy. And we're going to look at the very important case of the change in energy for a charge moving between two charge plates through the electric field set up in between. So what we do with this is we integrate the equation. And just to remind you, that is delta U equals negative integral QE dot, remember, scalar product of two vectors, the displacement. And then we interpret our results. And we're also going to walk away from this with the reinforced idea that electric fields are conservative, that the motion between two paths is independent of the path taken. The change in energy for a motion between two paths is independent of the path taken. So we start out with our two charge plates. And let's say this one is positive and this one is negative. And what we're going to do is we are going to take a positive charge and we are going to move it from the negative plate over to the positive plate. The electric field in between the two plates is uniform and points out of the plus and into the minus. And it's going to have a magnitude sigma, the charge per unit area, over epsilon naught. And the direction in this case is going to be left to right. So I'll just indicate that real quick with an I here, although we're going to largely ignore that once we justify why we can. Okay, so we start out with our equation. Our change in potential energy between the two plates is going to be the negative of integral Q, and in this case, let's say we're going to move a proton. So the positive fundamental charge times E, which in this case is sigma over epsilon naught in the positive I direction. And our displacement dot our unit vector in the direction of the field. So all of these terms are constant. We can move them out in front of our integral sign. So we can rewrite this as negative E sigma over epsilon naught integral, really I dot ds. So we take a look at our dot product here. And what this tells us is that only components of ds that are parallel to I, in other words, in the x direction, are going to survive. And we know that because the general formula for a dot product is that magnitude A dot B is equal to magnitude A, magnitude B, cosine of the angle between them. So in the x direction, that cosine term is going to be 1. And the y and z direction, that cosine term is going to be 0, because the electric field is purely in the I direction. So this entire thing here, we can rewrite as negative E sigma over epsilon naught integral dx. And the integral dx in this case is just going to be the displacement in the x direction, which I will call capital X. So, however far we were to move in the y or z direction, and whatever crazy path we took, the only thing that's going to matter between those 2 points, the only thing that's not going to go to 0, is that term x. So the change in potential energy as we move a charge between those 2 points is simply going to be negative E sigma over epsilon naught times x. Or, in more general terms, for parallel plates, delta U is going to be negative Q E times the distance traveled, so we'll just turn that into a D. So this is a nice general result for parallel plates.